Hello, my name is Coby Wang. I'm a PhD student in the Department of Computer Science at UNC Chapel Hill. Today, I'm going to introduce Amnesia, a framework to detect credential database breaches. This is joint work with my advisor, Michael Reiter. Passwords leaked from data breaches have been a major threat to web security. According to a recent Verizon report, nearly 4,000 database breaches happened globally between November 2018 and October 2019. And 60% of those database breaches leaked credentials. Recent reports by IBM show that an organization will experience a data breach in the next 2 years with likelihood about 30%. And it takes on average 207 days to identify a breach. In 2013, Jules and Rivas proposed the Honeywords scheme to detect the breach of password databases. The general idea of the Honeywords scheme is to hide the user's password with a set of decoy passwords called Honeywords. These Honeywords are generated in a way that if the passwords are leaked from the database breach, it should be difficult for the attacker to figure out which is the real user password. To tell if a submit password is real or decoy during authentication, the website needs to store the index of the real password somewhere at the web server. During each login attempt, if the submit password is one of the passwords stored in the database, the website could compare its index with the real password index to determine if the submit password is a honeywords or not. However, if the index is stored along with the user's passwords in the database breach would also leak the index, so the attacker could learn which password is real. To deal with this problem, Jules and Rivas' Honeywords proposal uses a second component called honeychecker to store the index of the real password for that user and assumes that the honeychecker remains secure even if the passwords are leaked. Since the real password index is well protected at a secure honeychecker, the breach attacker is unable to figure out which password is real without access to the index, and a submitted password with a wrong index will trigger a breach alert. It's not hard to see that the detection power of the Honeywords scheme relies on the assumption that the honeychecker is secure. This strong assumption limits the original Honeywords to be practical in the sense that if the website could deploy such a secure component, why wouldn't the website directly store users' password as a secure component in the first place against possible breaches without the necessity of using any decoy password at all? In other words, the idea of using a secure component of the web server to protect secrets about user password to defend or detect password breaches already assumed away the original problem. So now the question is, can we use decoy passwords to detect credential database breaches without relying on any persistently stored secrets? The answer is yes. The first major contribution of our paper is a new Honeywords scheme to achieve this. The second major contribution of our paper is related to credential stuffing. Credential stuffing has become one of the effective attacks to steal user accounts. During the attack, an attacker tries to log in with a breach of credentials at other sites, and it would get access to users' accounts if the user reuses their passwords across those sites. What's worse, credential stuffing could be very helpful to avoid detection by the Honeywords system. For example, if the attacker tries to log in at site B with the passwords leaked from site A, and if the user Alice reuses her passwords, then a successful login at site B would indicate that the submitted password is the real password for Alice's account at site A. The attacker can then submit the real passwords to site A without risk of being detected by its Honeywords scheme. In our paper, we propose a framework to deal with the two obstacles the existing Honeywords scheme is facing today. First, our framework can detect credential database breaches without relying on any persistent secret state. Our framework can also detect credential database breaches, even if the attacker attempts to avoid detection by stuffing the breach passwords at other websites. Here, we introduce our framework, Amnesia. The reason we name it Amnesia is that it can help websites to detect password database breaches without relying on any persistently stored secrets. In other words, Amnesia allows the attacker to learn all persistently stored secrets at the website, but it still can detect the breach. Like the original Honeywords scheme, Amnesia requires the websites to store the real user password along with its decoy passwords. But instead of storing the index of the real password somewhere at the server, the website executes the following marking process after each successful login. It marks the last submit password and marks each of the other passwords with a preset probability. Here you can think marking as a flipping associated bit to 1 for that password. During a login, if the submit password is one of the marked passwords in the database, then the login is successful with no breach alert. However, if the submit password is one of the unmarked passwords, Amnesia will report a breach alert. So the core idea of Amnesia is that normally the user is expected to submit the real password, so the real password should remain marked most of the time. But a marked Honeywords submitted by the attacker, which is password 4 in this example, would affect the probability distribution of the real password being marked after this login. So after this attack, the Honeyword password 4 will remain marked, but with some probability, the real password, password 2, will left unmarked. Then the user's next login with a real user password will set the alarm off because it's unmarked. In our paper, we use probabilistic model checking to evaluate how Amnesia would accelerate discovery of a credential database breach. This is a curve from our model checking experience. The y-axis is benefit brought by Amnesia. Informally, benefit is the expected fraction of time that Amnesia deprives the attacker from accessing user accounts before discovery of the breach. The x-axis is the number of the Honeywords deployed for a user account. The curve shows the benefit as a function of number of Honeywords for user account. We can see from the graph that the benefit can reach up to 0.5 under certain parameterization if the number of Honeywords is about 200. This means that Amnesia can deprive half of the attacker's time to access users' accounts with leaked passwords before detected. Please refer to our paper for more detail about the experience. What needs to be mentioned here is that our model checking experience is conservative in the sense that, first, the evaluation in our paper is for one account only. But in practice, the attacker would attack more accounts, and one mistake at any of them would trigger a breach alert. Also, the model checking experiment computes benefit for the best possible attack strategy. The second major part of our work is to extend Amnesia to detect password database breaches against attackers who attempt to stuff the breached Honeywords at other sites. To deal with stuffing of Honeywords, we propose a framework that can convert remote stuffing to local online guessing. In other words, while proper communication between site A and B, the attacker's login attempts at site B with a linked password from site A can be seen as if the attacker directly tried those passwords locally at site A. In our paper, we call site A the target and site B the monitor, since site A is the attacker's breach target, while site B is monitoring for site A about its Honeyword submissions. To protect account security at both parties and avoid false alerts, we also specify the following security goals of our framework. First of all, the framework should not leak any of the target's stored passwords to the monitor. Secondly, the framework should not leak the submit password as monitor to target if the password is not one of the target's stored passwords. Also, the framework should not allow the monitor to trigger a false detection if no breach has happened to target. In our framework, we use a two-party secure computation protocol named Private Containment Retrieval Protocol, or PCR protocol, to achieve the functionality and security goals. During execution of a PCR protocol, target inputs a set of passwords while monitor inputs a password. If the target's input set contains monitor's input password, then the target could retrieve the monitor's input. Otherwise, it learns nothing. Monitor learns nothing in either case. In our paper, we propose a PCR protocol construction that is tailored for our framework. It's based on partially homomorphic encryption and Cuckoo filters, and requires only one round of interaction. This PCR protocol meets all three security requirements and have some performance benefits that I will introduce later. To convert remote stuffing to local online guessing, target first generates a PCR query on all of its stored passwords and send the query to the monitor. After receiving the PCR request, the monitor generates a PCR response for each password submitted in the failed login attempt at monitor. Then the monitor sends the PCR response back to target. Upon receiving a PCR response, target tries to retrieve the submitted password in the response, if the submitted password is in target's password set. then the target will be able to retrieve it. Then the target just treats the password as a submit password received from a local login and run the marking process accordingly. In our paper, we empirically evaluated the performance of our PCR protocol. Considering that the PCR query message is a one-time message during monitored setup, while the PCR response is generated in per login level, so it would become the bottleneck more easily. In this talk, I will mainly introduce performance evaluation results related to response messages. The PCR response generation time for monitor is constant in the number of targets input password, which is the number of Honeywords plus 1. For example, in our experiment, it only takes about 9 milliseconds for a single core CPU monitor to generate a PCR response with equivalently 128 bits symmetric security. PCR response revealing time for target is also constant in the number of target stored passwords if the response does not include a Honeyword, which is expected to be the usual case. In our experiment, it only takes about 3.5 milliseconds for a single core CPU target to determine that a PCR response doesn't include any of its stored passwords. In terms of communication cost, the PCR response message size is constant in the number of target stored passwords. For example, the PCR response message size with equivalently 128-bit symmetric security is about 1 kilobyte. Please refer to our paper for more detail about our empirical performance experience. To summarize this talk, we propose a new Honeyword framework named Amnesia, which can detect password database breaches without relying on any persistent secret state. We also extend Amnesia's ability to detect password database breaches if the attacker tries to bypass detection by stuffing breach Honeywords at other sites. To achieve this, we propose a new two-party private containment retrieval protocol and use the protocol to convert remote stuffing of Honeywords to local online guessing. Our evaluation results showed that Amnesia would substantially shorten the time between credential database breaches and their discovery, and our PCR protocol is practical and well suited for Amnesia. Thank you.